So we're going to talk about properties of sampling distribution. So let's first talk about what in the world a sampling distribution is. So sampling distribution is the probability distribution of a sample statistic, all right, that is formed when random samples of size n are repeatedly taken from the population. So say we have some population with a mean of mu and a standard deviation of sigma, okay? So I'm going to do one random sample, all right? The first random sample has a mean x bar 1. Now I'm going to go out and I'm going to pick another random sample 2 and it has a mean of x bar 2. And I go out and I pick the same amount again for another random sample. Random sample 3 has an x bar 3. And I continue this process on and on and on and on. So each circle represents a random sample of size n. So each of those are random samples of size n. Okay, where if n was like 20, I go out and I ask 20 people, I don't know, how old are you, right? And I get an average. Then I go out and I ask 20 more people, maybe some are the same, maybe some are new people, but it's 20 more, and I ask them, how old are you? And then I go out and I ask another 20 people. Maybe some overlap with the first and the second group, but maybe they don't, right? Doesn't necessarily have to, but it's 20 people. That's the key. I'm going out and I'm randomly picking the same amount and I'm repeatedly doing it to form a population. What is my population I'm forming? I'm forming sample means. So I'm forming lots of sample means. I keep going out and getting new sample means, and those make up a population. So the sampling distribution of the sample means, okay, that's what I'm doing right there, for the sample size n for this population is, and that is x bar 1, x bar 2, x bar 3, right? That's the population. Now, properties, because we need to talk about properties here. So, properties of the sampling distribution of sample means. Now remember, sample means, that's just a fancy way to say x bar, right? Property number 1, the mean of sample means how do I write this? The mean of sample means is equal to the population mean. The mean of the sample means is equal to the population mean itself. So the mean of the original population was mu. So if I did the mean of all these means that I go out and I get, the average of the average, it says the average of the average is the original average. Interesting property, very powerful. Number 2, the standard deviation of the sample mean. So how these sample means vary, the standard deviation of the sample mean is equal to the population standard deviation divided by the square root of the sample size. Okay, so the square root of sample size. So the standard deviation of sample means, that's how we read that, is equal to the population standard deviation divided by the square root of the sample size. Okay, the square root of the sample size, how big the sample was that we went out and picked. Remember I was saying in here, this was based off like of an n equal to 20. So I would take that standard deviation and it would be the standard deviation divided by the square root of 20. Okay, whatever that is. Heck, I don't know, like 4.5 or something like that, whatever. Maybe not. All right, so standard error of the mean, another definition, this is the standard deviation of the sampling distribution of the sample means. All right, so it's just another way to say this right here. That's the standard error, okay? Error, I think, is standard deviation in terms of error, how far off from the true mean we are, okay? So let's do an example where we illustrate this property, these two properties, which are very powerful. So the first, this example, the first part, we've got the number of times 3 different people go to the grocery store in a month. So one person goes 1 time a month, another person goes 3 times a month, and the third person goes 5 times a month. These are the population values. Now, the population values, okay? So what we're going to do is we're going to randomly select 2. So our n here, our sample size is going to be 2. And I want to list all possible samples of size 2. Now, with this list, I can pick the same person more than once, but I can only pick 2. So I've got my sample, and then I'm going to have my sample mean, my x bar. Okay, that's what I'm looking at, my x bar. Now, the sample, if I pick the same person twice, I could pick the 1 both times. So I could pick a sample of 1 and a sample of 1. The average for 1 and 1 is 1. The next sample I could pick 3 and I could pick 3 again, right? And that average is 3. The next example, I could pick 5 and I could pick 5 again, and that gives me an average of 5. So that gets all my doubles right there. But now I could pick what? I could pick a 1 and a 3. Average of 1 and 3, well, 1 plus 3 divided by 2, that's 2. Okay, I could also pick a 3 and a 1, so that's going to get me 2. I could pick 1 and 5, and that average gets me 3. I could pick 5 and 1, and that average gets me 3. And is that everything? Let's see, 1, 2, 3, 4, 5, 6, 7. Okay, I think I might be missing. All right, so 5 and 3, that's going to give me an average of 4. And then 3 and 5, I think that's all of them, okay? How do I know how many total there are? Well, let's think about it. How many is a counting question, right? Well, if I'm doing how many, I'm selecting 2 people, so there's 2 positions. I have 3 to choose from on the first one. And then since I can replace and pick the same person, I'm drawing with replacement, right? I can pick the same person again. There's 3 to choose on the second one. So how many total? That's 9 total. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's all of them. So these are my averages. These are the values. Okay. If you want to say X bar 1, X bar 2, X bar 3, X bar 4, X bar 5, X bar 6, X bar 7, X bar 8, and X bar 9. Those are all the sample means from randomly selecting 2 out of 3 people. Okay, and we're drawing with replacement. So what do I want to do? I want to find the mean of the sample means. The mean of the sample means is equal to, well, I got to average all of those numbers, right? So let's do it. So 1 plus 3 plus 5 plus 2 plus 2 plus 3 plus 3 plus 4 plus 4. All divided by 9. I add that up, that's 27 over 9, which equals 3. Okay? The standard deviation of the sample means is the sum of x minus the sample mean squared over, and we'll say n here. Okay, so the mean, all right, so let's do the mean here. Okay, and so what's that going to be for us? Well, my mean is 3, so the first value is 1. So I do 1 minus 3 squared. And the next one is 3, so 3 minus 3 squared. And then I have 5 plus 5 minus 3 squared plus 2 minus 3 squared plus 2 minus 3 squared plus 3 minus 3 squared plus 3 minus 3 squared plus 4 minus 3 squared plus 4 minus 3 squared, all divided by how many there are. There's 9 of them. Oh my goodness, that's a lot, right? So to save you a little bit of work, the numerator is 12 and the denominator is 9, so that gets me 4 over 3. To get the standard deviation, I take the square root of 4 over 3, and that's 2 over the square root of 3. 2 over the square root of 3. So this is the standard deviation of sample means is equal to 2 divided by the square root of 3. Okay? Yikes. All right? So a little bit of work there. Now, there is a much faster way to get these numbers, okay? That's a lot of work, right? There's got to be a better way. So let me show you the better way than doing all this work here. Use the properties of the sampling distribution of sample means. Okay, what is the property? The mean of the sample mean is equal to the original population mean, and the standard deviation of the sample mean is equal to the standard deviation divided by the square root of n. All right, what was it? It was the original population was 1, 3, and 5, right? That was the original population. Now, the original mean, all we have to do is average 3 numbers. Wow, that's pretty tough. That's 9 divided by 3, which is 3. So the population mean is 3. So the mean of the sample mean is equal to 3 by definition. Was that what we got? Yeah, but we had to average 9 numbers and we got 3. Not too bad, but this one was a booger, right? That one was really hard to do. I mean, it's a lot of work writing all that stuff out. And that was only selecting 2. Imagine if we'd selected 20. Oh my gosh, it'd be crazy. Okay, so standard deviation of the population. Well, the standard deviation is equal to, it's the sum of the x value minus the mean squared over n, right? So how do I do this? Well, it's 1 minus the mean 3 squared plus 3 minus 3 squared plus 5 minus 3 squared over, well, what was the mean? It was, I'm sorry, how many was it? There's 1, 2, 3 total, so n is equal to 3. If I do this, this is negative 2 squared. That's 0, so that goes away. And that's 2 squared. So that's 4, and this is 4, so that's 8 over 3. Okay, that's the variance. To get the standard deviation, I take the square root of 8 over 3. Now, you don't have to know this, but the square root of 8 is actually 2 square root 2. And the square root of 3, we're just going to leave as the square root of 3. Now, why does that do that way? 2 times 2 times 2 is 8. But 2 times 2 is 4, so that comes out of the radical, and then the other 2 stays inside. That's why that works the way it does, okay? So, but what does the formula say? It says the standard deviation of the sample mean is equal to the standard deviation divided by the square root of n. Well, what is this? Well, it's 2 square root 2 over the square root of 3 divided by the square root of n. Now, n is the sample size, right? The sample size is 2. We randomly select 2 with replacement. So I divide by the square root of n. And when I divide fractions, I keep change flip. I keep the numerator the same. 2 square root 2 over square root of 3. I change division to multiplication. And I flip the denominator to do the reciprocal 1 over the square root of 2. And guess what? Those square root 2's cancel. And I get 2 divided by the square root of 3 for my standard deviation of the sample means. Is that what I got earlier? With all that work in here, yes, I got 2 divided by the square root of 3. So as you can see, this way, using the properties is faster than if you were going to try to do it using it, just muscling it out, okay? And one thing I want to show you is the population distribution, okay? So here we had 1, 3, and 5. So the population of the values, the x's, was 1, 3, and 5, right? So what is that? Well, there's a 33% chance we have a 1. There's a 33% chance we have a 3. And there's a 33% chance we got a 5. Now, technically, it's like 3, 3, 3, 3, 3, right? Repeating, it's 1/3. So when you're going to get rounding error there. But that's the idea. This is a uniform distribution, equally likely for each of those, okay? And this was, the population mean was 3, and the population standard deviation was 2 square root 2 over square root of 3. Now, what happened whenever we converted to the population for the sampling distributions of x bar, right? How many x bars did we have? We had 9 of them. There were 9 values. Okay? So I had 1, 1. I had 2 2s, I think. 2 2s. And then 1, 2, 3 3s. I had a 4 and a 4, and then a 5, okay? That was the population distribution. This is the sampling distribution for the sample means, all right? So we went from values of x's to values of x bars, right? So very important, right? So what's happening here? My distribution now, there's 1 out of 9. So 1 out of 9 for a population of 1. that's like a 0.11. To get a 2, that's 2 out of 9. So that's like 0.22. To get a 3, there's 3 of those. 3 out of 9 is 1/3, so that's 0.33. There's 2 4, so that's 2 out of 9, that's 0.22. And then 1 9, that's 1 5, and that's 1 out of 9, which is 0.11. So when you look at the distribution compared with the x, look at the new x bars, the sample means. What do you notice about our distribution? It's definitely mound-shaped. It's looking more and more normal. And that's only with n equal to 2. Okay, that's only with n equal to 2. Right? So very, very powerful here. So what's happening? As my n increases, as the n increases, okay, the distributions become more and more normal. Okay, so they become more and more normal. So they look more and more normal like this. They follow a normal pattern. So that's the idea, right? And in the next video, we'll talk about what that cutoff is.